Let's take a look at limits. And kind of introduction to this. I always give this example in class. It's not a very business-oriented example or medically-oriented example, but my wife used to have this dog. He was a Carrion Terrier, Rat Terrier, the little Toto dog. Not a very smart dog. And we had a German or have a German Shepherd also. She's still alive and very smart dog. Well, one time I had both those dogs out there, and I am getting ready to barbecue, so I take the grill off, lean it against a tree, and I get ready to clean the charcoal out. And I look over there, and that little dog of hers has got his leg raised, and he's wetting down my grill for me. Well, I see red. I pick up the hard plastic chair sitting next to me, and I throw it at the dog with the intention of killing it. Well, the moment it left my hand, one of two things would have happened. I would have killed the dog, hit it and killed it, and then I would have had to bury it somewhere and tell my wife I don't know where her dog went to, because she loved that dog more than me. He's passed away now. Or the other thing would be miss the dog and break the chair. Well, I missed the dog, broke the chair, which is good, very good. So I hid the chair in a shed, and I think my wife discovered it a couple months later. She didn't say much. I think she thought maybe one of the kids did it. But I think if she'd known I'd done it, she would have been pretty upset, and I would have heard about it for quite a bit. The idea of limits is we don't care what's happening at that point, because at that point that chair flew out of my hand. But if we could study it going up to that point, if I could have studied my anger and thought, okay, urine washes off, maybe the hamburgers just taste extra special that day also. I don't know. It wasn't that big of a deal. I should have set the chair down and went on. Learned not to put the grill down when he's outside, because otherwise he's going to wet him down for me. Another example. This one's more medically related. Somebody's going in, and they're having some heart problems. So here their heart's going along, it's getting bigger like this, and all of a sudden here's a heart attack. And then it goes off in that end. Now, it's not that important for the hospital to monitor this part right here while they're in the middle of the heart attack. Because as I understand it, heart attacks aren't real lengthy processes. It's not like a half-hour event or an hour event. But if they could study it leading up to that, then they could see this build up maybe, and they could give them some medicine to stop it. I've been told nitroglycerin is what they give. Maybe they could stop that heart attack. Over on this side, again, studying it on this side is important because especially if it's going this way, you could be leveling off like that where you need to give them something to stimulate the heart, or they're getting ready to have another heart attack. So again, it's not that important while it's happening, but important studying up to it and after it. My dad had a stroke that took 50% of one eye and 75% of the other eye. While he was having a stroke, it was a very short event. Didn't take very long at all. It's not something you could probably even study. But leading up to it, if they had done some studies and found the blood flow and so forth, he actually had one of his eyes go kind of half blind. And the doctor said after he had the stroke that was actually a signal. So again, important studying up to it. This is a concept of limits. We don't care what's happening at that point, but we're studying it as it's leading up to it, and on the other side also. Let's take a look at a problem here. So we got limit. Then you got the x with this arrow, and then 2. And then x squared plus 4x minus 1. Now, this is limit as x approaches 2, and of x squared plus 4x minus 1. And we got a table here. And our first x value is 1.9. Next one is 1.99. Next one is 1.999. and we're wondering what's happening at 2. Now specifically, we're wondering what's happening as we approach 2, and then from the other side too. So we're getting closer and closer from the left side to 2, and from getting closer and closer from the right side. So we're wondering what this limit is. Again, this is not what is the value at 2. It might not even exist at 2. We're studying it as it gets closer and closer. Well, let's do 1.9 first. Okay, so for x equals 1.9, we come up here and we put into our algebraic expression, the x squared plus 4x minus 1. So I have 1.9 squared plus 4 times 1.9 minus 1. I'm going to put that in my calculator. So I got 1.9 squared plus 4 times 1.9 minus 1. Enter. And that gives us 10.21. Now that's kind of tedious to go through there and do that for every data point. Let me show you an easier way using the TI3, TI4. If I come here, and I'm going to go into a table set, which is second, and then whatever that button says, window. And see how it's table star, table, this delta table, independent, dependent. I'm going to down arrow to the independent line, and I'm going to right arrow to the ask, and put my flashing cursor on the ask, and press enter one time. You should see the highlighting go off from the auto to then go to ask. Now I want to go to table mode. So I do second graph. Now this is where we're going to actually input our x values. So we set up our table. This is where we're going to input them. So we're going to go to y equals, press clear, and I'm going to put in x squared. So x key, x squared plus 4x minus 1. Okay, go into table. And then we're going to put in 1.9. First, let's look at that one. We already did that one, but 1.9, and you see we got 10.21. Now put in 1.99, and we get 10.92. Then we're going to put in 1.1239, enter. We get 10.992. Now from the other side, start with the one furthest away of the 2.1. Do 2.1, enter. And that gives us 11.81. Then 2.01, enter, and we get 11.08. And then 2.001, enter, and we get 11.0008. Well, as I'm studying it coming from the left side, looks like it's getting closer and closer to 11. And as it's coming from the right side, looks like it's getting closer and closer to 11. So our answer will be 11. Now it has to agree coming from the left and from the right. And I'll write that note up here in a little bit once we start looking at the graphical representations of these. Anyway, that's our answer is 11. Let's look at our second example. We get the limit as x goes to 3 of x squared minus 9 over x minus 3. And we got 2.9, 2.99, 2.99, well, 3 nines, and I think 3 is what we're wondering about. And then over on this side, we're going to have 3.001, 3.01, and 3.1. Well, how close do we need to go? 2 and then 3 nines? Maybe we need to do 2 and then 4 nines. I don't know. It probably depends on the problem. Now, anywhere in your graphing calculator where you're plugging in a fraction and you have more than a single x or single number on top or bottom, you have to put parentheses around that. So have more than a single term up on top, so I have to put parentheses around that. And more than a single x or single variable down below, so I have to put parentheses around that. So that's how we're going to enter it. So let's come over here. I press my y equals, clear, do my beginning parentheses, x squared minus 9, closing parentheses, divided by beginning parentheses, x minus 3, close parentheses. Now go to our table. So I do second graph. Now I have the old data points there. You can press delete over and over to clean those out. And let's put our new ones in. So we got 2.9 inner, 2.99 inner, 2.999 inner. So we write these down. So I got 5.9, 5.99, and then 3 nines. Looks like it's approaching 6, doesn't it? But let's see. On the other side, 3.1. So 3.1 inner, 3.01 inner, and 3.001. Okay, so we get 6.1 here, 6.01, and then 6.001. Now again, we're not looking at what is its value at that point. We're looking at as it gets closer and closer, coming from the left side and from the right side, and they have to be approaching the same value, and these both appear to be approaching 6. So 6 is our answer. Now you notice that this doesn't actually exist at 3. If I put 3 in, I have 3 minus 3 in my denominator, and that gives us 0. So that doesn't even exist there. Okay, that's a table method of limits. We also got some graphs. So let me write this down. So we got 1, 2. We got 2, 8. 3, 4, 5, 6, 7, 8. I don't know, something like that. And the first thing we're looking at is the limit as x approaches 1 of f of x. Okay, so here's 1. X equals 1. And we're studying it as it's getting closer and closer to x equals 1. Now there I'm coming from the left side, and here I'm coming from the right side. Now as I get closer and closer, come from the left side, and closer and closer, come from the right side, when we're asking what this limit is, we're asking what is the y value? Well, both of them are approaching 2. So it'd be 2. Now again, this one you could say, well, it is 2 at 1, but we're studying it as it's approaching from left and from the right. Now if they don't agree coming from left and from the right, then it does not exist. And this one was 2, 8. Yeah, limit as x approaches 2 of f of x. Well, coming from the left side, it's getting closer and closer to it, and then come from the right side, it's getting closer and closer to it. Whether I'm coming from the left side and from the right side, they're both approaching, in terms of my y value, they're both approaching 8. So 8 would be my answer. Save that. This is limits. And let's look at the next problem. Okay, let me draw it. Looks like 1, 1, 1, 2. So 1, 1. And then 1, 2. Look like that. And then it says c is equal to 1. And then it's asking us to find a limit as x approaches c, which looks like the positive power, f of x. And then limit as x approaches c, looks like the negative power, f of x. Then limit as x approaches c of f of x. Well, that plus is not really plus power. This is from the right-hand side. So that's going to be from the right-hand side. And this negative here will be from the left-hand side. Okay, so let's look at that. Now I'm getting closer and closer, and if I put c is equal to 1, if I put 1 in here, we're getting closer and closer to x equals 1, coming from the right-hand side. Okay. So here I am coming from the right-hand side. I'm getting closer and closer to x equals 1. And as I get closer and closer, my y value is going to equal to 2. Now from the left-hand side. Okay, I'm getting closer and closer to x equals 1 from the left-hand side. And if I look over, my y value is going to be a positive 1. Now notice how they do not agree coming from the left-hand side and from the right-hand side. So this does not exist, D and E. Again, your graph has to agree coming from left side and from the right side at a particular point for the limit to exist. Now we got some different techniques we'll look at. So let's look at the first one. These are ways of evaluating algebraically limit. And the first one is direct substitution. So we got 6. And we got limit as x approaches negative 3 of x squared minus 3x. If it doesn't specify any other method, the first one you should try to do is direct substitution, because it's so simple. With direct substitution, what you do is you take this value, the negative 3, and you plug it in for your x. So we got negative 3 squared minus 3 times negative 3. Negative 3 squared is 9. Negative 3 times negative 3 is 9. And so our answer would be 18. So again, just plug it in. Let's look at another one of those. We got the limit as x goes to negative 1 of 4x minus 1 over 3 minus x. Again, I'm going to use direct substitution. So where my x is, I'm going to put in negative 1. So I got 4 times negative 1 minus 1. And I got 3 minus a negative 1. Well, 4 times negative 1 is negative 4 minus 1. And down here, a negative negative becomes positive, so we've got 3 plus 1. Negative 4, negative 1 is negative 5, and 3 plus 1 is 4. So our answer is negative 5/4. One more direct substitution. Then we'll look at the next type. Limit as, oops, what did I just do? There. Limit as x goes to 4 of 1 over x plus 3 minus 1 over 3 all over x. Well, again, we just plug in our number. So we got 1 over 4 plus 3 minus 1 over 3 all over 4, which gives us 1/7 minus 1/3 over 4. Now this is a complex fraction. The one method that works 100% of the time in getting rid of a complex fraction is to multiply everything by the LCM of all your inner denominators. Now when I say inner denominators, I'm talking about the fractions inside. So that'd be 7 and 3. So our LCM of those would be 21. So we'll multiply everything by 21. So 21 times 1/7 minus 21 times 1/3 all over 21 times 4. Well, 7 and 21 both divisible by 7. 7 divided by 7 is 1. 21 divided by 7 is 3. 3 and 21 both divisible by 3. 3 divided by 3 is 1. 21 divided by 3 is 7. So we got 3 times 1, or 3, minus 7 times 1, or 7, over 21 times 4, which would give us 84. Now, top part, 3 minus 7 is negative 4 over 84. Top and bottom both divisible by 4, so that gives us negative 1 over 21. And that's our answer. And let me save that and go to the new page. Oops. And time for that to blow up, so I'll bring up a new tablet. Okay. This next one's going to be the factor cancel method. It's a name I made up for it. Books never really do give it a name, and I thought it should have one. So limit as x goes to 4 of 2x squared minus 9x plus 4 over x minus 4. Now the problem with direct substitution here is if I put 4 in for my x, I'd have 4 minus 4 down in the denominator. You can't have a 0 downstairs. So what we're going to do, this is the factor cancel method. First step is to factor the top, factor the bottom. So factor the numerator and factor the denominator. Well, this is the key number on top. X squared x, no x, there's number for your x squared. And then the bottom part is nothing. So limit as x goes to 4, and this would factor as 2x, x, 4, 1, negative, like that. Then our second step, cancel if possible. Well, notice how these both have an x minus 4. So x minus 4 is going to cancel. So then we got limit as x goes to 4 of 2x minus 1. Well, our third step, plug in our value and simplify. We can use direct substitution now. Well, we're studying limit as x goes to 4, so we'll put 4 in for the x. So I got 2 times 4 minus 1 gives us 8 minus 1, or 7. And that would be our answer. Let's look at another one of these. So we've got limit as x goes to negative 3 of x squared minus 4x minus 21 over x squared minus 9. Well, direct substitution right away wouldn't work. Because if I plug -3 in, I'd have a -3 squared downstairs, which is 9. 9 minus 9 would give me 0, so we can't have that. Now this top one is the PSD method. X squared x, no number for the x squared. And the bottom part is the difference of two squares. Dots method. Two terms in my string it. Now we'll always write down what method of factoring so you can refer back to it later, but I won't show the steps anymore. This one's x minus 7 times x plus 3. And this one is x plus 3 and x minus 3. Now remember, our second step said to cancel if possible. Well, this has an x plus 3 and this has an x plus 3, so those are going to cancel. And we got limit as x goes to -3 of x minus 7 over x minus 3. Well, now if I do my direct substitution, it works out a lot nicer. So I put -3 in the top, so I get -3 minus 7 over -3 minus 3 down below, which gives us -10 over -6. The negatives cancel. 10 and 6 both divisible by 2, so that gives us 5/3 as our answer. Excuse me. And that's factor cancel method. Now these next problems revolve around piecewise functions. Now let's look at this first one, and then I'll talk more about what a piecewise function is. The first one's kind of an oddball case. Limit as x approaches 2 of f of x, and f of x is equal to 3x minus 1 and 7. This is when x is not equal to 2, and this one is when x is equal to 2. Okay. Well, we're studying limit as x approaches 2. Now we could care less what happens at 2. So we could care less about this one. We don't care what's happening at 2. We're studying it as it's getting closer and closer from left side and from the right side. Well, after I cancel out that one, which is exactly 2, we're only left with this one, so we can use direct substitution. So I'll put 2 in for the x, and I got 3 times 2 minus 1, which gives us 6 minus 1, or 5. And that'd be our answer. Now, when I say that's the oddball case, well, that's when you have an equals and not equals on your conditions at the end. But let's now look at the normal piecewise functions and understand what's going on with them. So let me save this one. Why does that keep doing that? Okay, for a piecewise function, you got two possibilities. You got a line coming here. It ends there. It's only true from like x is less than 2 or whatever. And then up here, it's looking like something else. They don't meet. This would tell us that the limit doesn't exist, because coming from the left side and from the right side, they don't agree. So the limit here does not exist at this value right here. On the other hand, if it's coming here, stopping there, then the other one is continuing on like that. As they're coming from the left side and from the right side, then the limit does exist. So the key point on this is we're going to study what's happening from both sides, from the left side and from the right side, and see if they agree. So let's take a look at that. That was that one. Let me look at the next one. Uh, 12. I got limit as x goes to 3 of f of x. And then f of x is equal to this piecewise function here, 5x minus 1, negative x plus 17. And this is when x is less than or equal to 3, and this is when x is greater than 3. Okay. I don't know what this graph looks like, but x is less than or equal to 3, so this is coming from the left-hand side, getting closer and closer to 3. And this one is x is greater than 3, so that's coming from the right-hand side, coming closer and closer to 3. Well, what we're going to do is we're going to plug our 3 into both pieces and see if they're the same value. So put 3 in here. I got 5 times 3 minus 1 gives me 15 minus 1, or gives me 14. On this one, I'll put the 3 in for the x, so I get negative 3 plus 17, which gives us 14. Now these agree, and notice here, x approaches 3, and where they change is at 3. Now, if you're asking over here, limit as x approaches 1, then you just look to see which piece it's valid in. But if this here is a 3 and both of these are 3, then you're studying this right here. Now, since they agree, that means my answer to this is 14. Because coming from the left side and from the right side, they both equal 14. Okay, so let's look at another one. So we got limit as x goes to 2 of f of x. And they tell us f of x is equal to 3x minus 2 and 4x minus 1. X is greater than 2, and x is less than or equal to 2. Well, the x is less than or equal to 2 is coming from the left side. X is greater than 2 is coming from the right side. So let's plug it into both pieces and see if they agree. And again, notice how they match. Here's 2, and these are 2. All 3 of those have to be the same value for this to work. So I'm going to plug my 2 in using direct substitution. So I got 3 times 2 minus 2, 6 minus 2 or 4. And I got over here 4 times 2 minus 1, which gives me 8 minus 1, or gives me 7. These don't agree, do they? So that means my limit does not exist. Because again, they have to agree come from the left side and from the right side. Let me save that. And let's look at the next one. There's nothing special on this one. This is just a little bit of manipulation. We're going to see a lot of these next chapter. The limit as this weird looking symbol goes to 0. And 9, and then x plus a weird looking symbol. Plus 2. Minus 9x plus 2 all over that weird little symbol. Okay. Here I am drawing myself. If I look where I'm at 2. Now I move myself over to the 6, and now I'm at 6. So x equals 2 and x equals 6. The change, the distance I moved, that's referred to as delta x. That's what that triangle is. Now this is not the same as the x values. That's not the same as x equals 2 and x equals 6. That's how much it's changed by. Okay. So the limit as delta x goes to 0. Well, obviously I can't use direct substitution because that'd give me a 0 downstairs here. But let's use some algebraic manipulation up on top. We use a distributive property. 9 times x is 9x. 9 times delta x is 9 delta x plus 2. And then the negative out in front of this parentheses flips the sign of everything. So it becomes a negative 9x minus 2 over delta x. Well, the 9x here cancels with negative 9x there. The 2 cancels with a negative 2 there. So we're left with limit as delta x goes to 0 of 9 delta x over delta x. Now remember, the delta x is just a variable, so the delta x will cancel there. And we got limit as delta x goes to 0 of 9. And this is so easy it's hard. Because people are used to direct substitution now, put 0 in for delta x. But there is no delta x. So our answer is just 9. Now this next one is a conjugate method. Let's look at it. We got limit as delta x goes to 0. The square root of x plus delta x minus 3 minus square root of x minus 3 over delta x. Well, obviously if I put 0 in for delta x, I get a 0 in denominator, which I can't have. So this is the conjugate method. What we're going to do is multiply the top and bottom, numerator and denominator, by the conjugate of the top. Now what makes me think of using this method in this particular problem is not because they say to use conjugate method, but because I have square roots. Oftentimes when you have square roots, this works out nice. So we got x plus delta x minus 3 minus square root of x minus 3 over delta x. Now what the conjugate is the first is the same and the second is the same, but the sign in the middle is different. So this will be square root of x plus delta x minus 3 plus square root of x minus 3. And again, what you multiply by the top, you multiply by the bottom. So this is square root of x plus delta x minus 3 plus the square root of x minus 3. Well, up on top, when you multiply conjugates together, all you have to do is multiply your first parts together and your last parts. So we're going to have square root of x plus delta x minus 3 times square root of x plus delta x minus 3 minus square root of x minus 3 times square root of x minus 3. Now down below, we're not going to actually multiply those together. We just put them next to each other. So that's delta x times the square root of x plus delta x minus 3 plus square root of x minus 3. Well, up on top, multiplying these together, since the radicals are the same, they cancel each other out, and you're just left with x plus delta x minus 3 minus, and then the square root of x minus 3 times square root of x minus 3 just gives you x minus 3 over delta x times square root of x plus delta x minus 3 plus square root of x minus 3. Well, up on top, we got limit as delta x goes to 0, x plus delta x minus 3. Negative out in front of the parentheses flips the sign of everything, so it becomes negative x plus 3 over delta x times square root of x plus delta x minus 3 plus square root of x minus 3. Now up on top, the x and negative x cancel. The negative 3 and 3 cancel. So we're left with limit as delta x goes to 0 of delta x over delta x times square root of x plus delta x minus 3 plus square root of x minus 3. Notice everything's multiplication downstairs. Well, not everything, but delta x times all of this. Since that's multiplication, then we can cancel these delta x's. Now, if I had a plus in there, like delta x plus that, you can't do that. Well, now we're ready to do our direct substitution because what was causing us a problem is now gone. So let's plug in our value. So we'll put 0 in for delta x. So this first square root is x plus 0 minus 3. And the second one is just square root of x minus 3. Which gives us 1 over square root of x minus 3 plus square root of x minus 3. Since square roots are the same, we'll add numbers out in front of them, which are invisible 1. So we got 1 over 2 square root of x minus 3. Now, I'm not sure where they leave the answer at. Oftentimes in intermediate algebra, we say we never want a radical left downstairs. But when we get into calculus, it actually works out nicer by leaving it down there. So we'll leave it down there. Not sure what the book actually does. But actually, I got one last one, I guess. Let's take a look at this one. The limit as x goes to 3 of 1 over x minus 3. Well, I can't use direct substitution. I can't factor and cancel. There's nothing really to factor. I can't use the conjugate method. There's no square roots of any sort. I could use a table method or I could graph it. Now I'm going to graph it just to make my life a little easier. Now remember with your graph, if you have a fraction, you have more than a single number or a single x in top or bottom, you have to put parentheses around that. So when I enter this, I'd put parentheses around the x minus 3. So let's graph this. I'm going to go y equals clear. Actually, let me press clear that. Okay, y equals clear 1 divided by beginning parentheses x minus 3, close parentheses, and graph. Now we're studying this as x approaches 3. So here's 3. Coming from the left side, it's going down, down, down forever. Coming from the right side, it's going up, up, up forever. Now, since they don't agree, my limit does not exist. Remember, your graph has to agree coming from the left side and from the right side at a particular number for that limit to exist at that number. So it does not exist. Let me save this. And we're done with that section.